Good day. Today's short session is on infiltration. What we'll do is calculate how much the wind pressure and density differences between inside and outside contribute to the infiltration of air into a building from the outside. Infiltration is defined as the uncontrolled airflow into and out of a building through small openings in doors, windows, and electrical plumbing penetrations. So this is just a schematic of a building. Outside temperature T0, inside temperature T sub I, and the squiggly lines are the airflow. Now, if we go and use the open system energy equation, where the heat loss is equal to the flow rate of air times its enthalpy difference, then we can actually write it in terms of temperature. The mass flow rate is converted into density times volumetric flow rate, and the enthalpy difference is converted to a C sub P times the temperature difference between inside and outside. And that's in kilowatts. So what we need to do then, if we know the temperature differences between inside and outside, we just need to compute the flow rate, drop it into this equation, and we get the heat loss directly. Now, I'll also introduce a new and related term called air changes per hour, ACH, and that's the flow rate of the air, flow rate of the infiltration divided by the volume of the building. And that will represent the amount of time it takes to turn over all the air in the building. Old buildings around 1, new buildings around 0.3 or so. So let's go ahead and develop an equation for the infiltration flow rate. You remember from fluid mechanics, the continuity equation just says that the volumetric flow rate is in area times velocity. This area effective is really all the crack areas around the doors and windows. And then the velocity we can get from Bernoulli's equation. If we know the pressure difference, that will give us the velocity squared. So what we can then do is just express the flow rate as a product of the area and the pressure difference to the 1/2. And there are two physical features that we need to consider. One is called the stack effect due to density differences between inside and outside. And the other one is the wind effect just due to the pressure of the wind on the building. So let's look at the stack effect. And here we just need to use the hydrostatics. The change in pressure with height is negative density times gravity. And in winter, this density difference is due to the temperature difference. If it's cold outside, the air is more dense. And then the slope of the outside pressure is more negative than the slope of the inside pressure. And what happens is if you just go ahead and just pick a point where the two slopes are equal, that will be at the atmospheric pressure, and that will form a horizontal plane where below this plane there's inflow because the outside pressure is greater than the inside pressure, and above the plane there's outflow from the building because the outside pressure is less than the inside pressure. So again, it's just the hydrostatic equation, assuming density differences between inside and outside due to the temperature differences. That creates a slope difference, which creates a pressure difference. And again, in a building, continuity always says whatever comes in, something else has to leave. So you always have to have a balance. So in this building, air is coming in below and leaving at the top. We can get an expression for the pressure difference by integrating the hydrostatic equation, and then we incorporate the ideal gas law, and that will then give us an expression for the pressure difference in terms of the temperature difference. And then we incorporate a discharge coefficient to add real-world effects across the cracks. And we also incorporate the fact that the neutral height h, that's here, that really occurs basically at half the height of the building. Again, since engineers are lazy, we'll just incorporate all of these terms, the discharge coefficient, the density, gravity, building height, temperature. That would be either inside or outside. It doesn't really matter because it's in Kelvin. And then we incorporate all that into a stack coefficient. And that stack coefficient, if we put in representative values, is about 0.015. The times the number of building stories. Finally, we look at the wind effect. Here's a plan view or a top view of a building with the wind coming in from the left. It stagnates, creating a high pressure on the left side. The flow is into the building, and then the flow leaves either at the sides or the lee side of the building. It turns out the lowest pressures are on the sides of the building, so they'll have the lowest, what's called the pressure coefficient. And again, using Bernoulli's equation, we can relate the pressure difference between inside and outside to the wind velocity, and then a roll load effect, which is the pressure coefficient. These two effects, the stack effect and the wind effect, are incorporated into the ASHRAE infiltration model, and they just are additive. So the flow rate is equal to the effective area times our stack coefficient times the temperature difference plus a wind coefficient times the velocity of the wind squared, and all that's to the 1/2, of course. The wind coefficient depends on the number of stories of the building and the surrounding environment. So look at your notes that you have for how to compute the wind effect, and then there is an example which you can then use to solve the homework problems. Okay, thank you.